All right, in this way, we start the 344th session of Tesos and Wi-Fi. Today is Monday. It's 5 in the morning here in beautiful Utah. I know for some of us it's early, for some of you it's late. You guys that come from the future, hopefully you had a very good weekend. I know you're like almost done with Monday, and some people are like, oh, it's Monday. It's Monday. It's a beautiful day, man. We're here and we're learning. That's a great day. Couldn't wait for Monday to come, man. Lots of stuff to talk about. This session is part of the free class of Wi-Fi design that Wireless LAN Professionals is delivering to you. All of the session, let me just share my screen here. Very quick. Here we go. All of the sessions get recorded and get uploaded to this website called the Wi-Fi of Things.com. So if you're new and you haven't been to the prior sessions, then all of the previous recordings we've had, the ones that we did in Spanish, the ones we have done in English, they're all here. Yes, I know we're in the 344th session. This is just, I don't know, 4th, 5th session that we've had in English about this class. It's right there where it says WLANPros Wi-Fi design class. If you just want to look at those sessions, then that compiles the ones we've done in English. The first session we had, the brief review, is about organizations that we as Wi-Fi professionals should be aware of. The IEEE, that's the Institute for Electrical and Electronics Engineers. And those are the ones who write standards, not just for Wi-Fi, for Ethernet 802.3. And then there is the 802.11 one, that is the 11th group that was created for people to make, engineers to make things work wirelessly. So that's what Wi-Fi is. There's also, that's not the only wireless communications. There's also another group, 802.15. So actually, if you go to IEEE.org, did I miss something? I think it was the Explore one, huh? IEEE, no, it brought me here. So they have standards for everything. Everything on the planet is basically has something to do with the IEEE. They have standards for, I mean, anything that has electrical or electronics in it, basically everything. So they write all those standards. We just talk about the 802.11 standard. And actually, I think I opened, there is a document. You can go there and register for free, create an account, and then you can download the standard. Like this one, for instance, is the 802.11 of 2024. They get ratified and modified and all these things that are happening once those amendments prove to, hey, this is going to work, and they ratify, that becomes part of the standard. They approve those amendments, and then you can get the document for free. Don't read it now. Read it later. It's only like 5,000 pages here. I don't have my eyes on me right now. Yeah, almost 6,000 pages. And it's boring. As most of the stuff that we do in this class, there's just no way to sugarcoat it. All of this stuff is boring. And today we're going to be talking about a really boring topic, modulation. But hey, you want to know Wi-Fi? You want to learn how it works? We got to learn all this boring stuff. So we're just trying to make it here not only free, but also just easy and simple. Because look, this stuff, I mean, who's going to read those 6,000 pages of stuff? And oh, here we go, you know, getting all these numbers and microseconds here and equations there. It's just a lot of stuff that is not that exciting. So companies like the Wi-Fi Alliance will get some of those standards. See, that's the other organization we talked about. And then they will just they will test those things for interoperability. So we go to wifi.org. Hey, one of you Boris, if you want to help me with this, just grab these links and paste them on the chat. Then whoever watches the videos later, they will get those links there. So if we go to wi-fi.org, see, that's the website, HTTPS. Actually, I can paste them as we go, but I'm going to mention more. So that's the website. Just paste it on the chat with the HTTPS and stuff. And then people will be able to just have them there in the session. So they test some of these devices and they test some of those standards, amendments to the standard written by the IEEE, and then they make it happen and create certification programs. And then if you have devices that they are the companies are members of the Wi-Fi Alliance, and then they send their devices and pay money, and then the Wi-Fi Alliance is going to test those devices. They're like, yep, this device works. Then they put the Wi-Fi Alliance seal of approval, basically demonstrating that they went through a certification program. See, they have different certification programs. And let me see if I have resources. Let's just look at Explore Technologies. So they have different type of different certification. See, Wi-Fi Easy Connect, Passpoint. Passpoint is a certification, and actually this is tied to 802.11u, an amendment of the IEEE. These guys come and test it and verify it, and then create like a Passpoint certification program. So if a device is Wi-Fi Passpoint certified, means that it can do what the 802.11u standard amendment to a standard can do. Wi-Fi protects it up, and there's many of these guys. The other organization we talked about on the first class was the FCC, or the regulatory domains in the US. The FCC.gov is the organization that regulates not just Wi-Fi, they regulate all frequencies, satellite radio, cellular communications, earth to space communications, radio, all the things that can be said and parts of the body that can be shown on TV, all that stuff, they regulate. And yep, they also regulate Wi-Fi. So as a Wi-Fi person, no matter where you are in the world, you should be aware and know about the IEEE, the Wi-Fi Alliance, and for us in the US, you have to know about the FCC. They have, I think the chapter or the section is, everything is under part 15. Oh boy, somebody look it up, Google it, and then paste it on the chat. It's part 15, something, anything that has to do with Wi-Fi. Somebody make the search for what is the part of the FCC that takes care of Wi-Fi.
Part 15 is radio frequency devices in general.
Okay, and then from there it just breaks down to many other stuff. So it's part 15 for something, I guess, what's Wi-Fi. Okay, just come back here, and then the next class we talked about radio frequencies, waves, and characteristics of waves, amplitude, frequency, phase, wavelengths, antennas. And antennas are those beautiful devices that brings these waves to us and allows us to send and receive waves. When talking about antennas, like if I want to make a search for the, let's say 9166 Cisco data sheet, those antennas will have their graphs and their antenna charts or antenna graphs or polar graphs listed with all of the capabilities of the antenna. We looked at the antenna patterns, the antenna graphs, and what this means is if you are looking at the access point like that, this is the radiation pattern, the area where that access point is going to be sending waves, sending energy. So that's cool that they put the AP on the graph so that you know if you're holding the AP like that, it means all around it, 360 degrees, it's the area where it's sending waves. in 2.4 and in 5. And then there is the vertical component or the elevation plane. If the access point is like this, of course, you know, the back of it is here. So it's mostly sending energy in this area. But yes, there is also energy on this part of the access point. Of course, you're not going to mount the access point like this. This is designed to be mounted in the ceiling like that. So most of the energy is going to be in here. Most of the waves coming from this access point is down here. That's what those graphs mean. And then we also talked about, so if you haven't watched any of these sessions, or if you were not here then, yeah, you probably want to go watch those later. And then we had another session on network interface controllers, NICs, how they work. And we had pretty good discussions about, you know, signals and how is it that the NICs work. And then the last one, for those of you who did not make it on Saturday, was about the contention process. What do devices in Wi-Fi have to do for gaining access to the medium and gaining access to sending waves? So that's another session you can watch later. And Arguidos Costaras. Hey, how's it going, Costaras? How's Greece this morning? Afternoon, whatever time it is for you now. He's there, but not there. Fine. All right. Any questions before we start? I hope you had a beautiful weekend, and I'm really happy you're here. Let's get going. We have, let me just probably get this guy going over here. And let's talk about modulations. Not contention, modulations. Wi-Fi uses different modulation. What's a modulation? Modulation is a way to encode data bits in a way that we're going to be transferring those back and forth in the air. So let me just look at my chat here, make sure that we have, thank you, Budis, for the Wi-Fi, they're all linked there. Also list the one for the IEEE. So, modulations. When we are sending waves, because that's what we started talking about since day one, is waves, what we're sending, what we're receiving. In the air, we're going to use a frequency. And pretty much since the beginning, when this Wi-Fi thing started, there was confusion about the word channel, because forever we knew that a channel is basically a narrow band frequency where energy is being sent, where waves are being sent. So if we get the energy from this narrow band transmission, so a channel, a narrow band transmission, like an FM channel, 88.1 or 106.3, all of those are narrow band channels. And when you get that energy from a narrow band and you spread it in multiple narrow band channels, then that's what's called spread spectrum, because you're spreading the energy in multiple channels in the spectrum. So direct sequence spread spectrum was one of the mechanisms used to transmit energy at the beginning. Now, there is another mechanism that was used in Wi-Fi, and it's called frequency hopping spread spectrum. Instead of just sending in multiple narrowband channels, it uses narrowband transmissions, but then it's not always on the same one. It just hops and switches to a different narrowband frequency. Frequency hopping spread spectrum is this mechanism used to also transmit ones and zeros to put energy in multiple different frequencies. This is what Bluetooth uses nowadays. There are many other technologies that use Bluetooth. If you use Bluetooth, then yeah, you're using frequency hopping spread spectrum. Once we get to the spectrum analysis class, we're going to be able to see the spectrum and see how these devices transmit and how it looks. And we're going to learn how to read the spectrogram and the frequency domain and the time domain and make sense of all these shapes and shadows and things. Frequency hopping spread spectrum and direct sequence spread spectrum were used for Wi-Fi at the beginning, okay? Now, this frequency hopping spread spectrum is another wireless technology. It is not Wi-Fi. It accesses the medium a different way. It transmits a different way. So we'll learn how to read all that stuff later. But in either technology, what we are doing is sending ones and zeros. Remember, in the air, it's not a Word document or an email. In the air, it's not data. In the air, it's not a segment or a packet or a frame or a byte or a bit or a one or a zero. In the air is nothing but waves. That's it. But then how is it that we're going to send ones and zeros? Because we're always talking about the digital age and then ones and zeros. How are we going to send ones and zeros using these waves? Well, we're going to play and use the characteristics of these waves. One of the characteristics is the amplitude. Remember how tall the waves are, how high they are, how much energy they carry. So we will use the amplitude to send ones and zeros. So if we send a loud, soft, the loud one represents a one. The soft one represents a zero. Ones and zeros, loud, soft, loud, soft. So that's what's called amplitude modulation. We're playing with the amplitude of these waves to send ones and zeros. We can also play with the frequency. How frequent are these waves going out? So we send a fast transmission that represents one, and if we send a slower transmission that represents a zero. Remember, the frequency is with what frequency, how often these waves are going out. So fast, 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 slow, slow, fast, 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 slow, fast. A fast is a one, a slow is a zero. That's frequency modulation, FM. Then we have phase modulation. If the wave goes from the center up, down, center, and that's a one, then you change the phase, and then instead of going up, you go down, then you're playing with the phase of these waves, and you're going to send ones and zeros that way. So these are ways that we use in Wi-Fi. Of course, this is not just Wi-Fi. All the technologies will use different modulations. In Wi-Fi, we use amplitude modulation, frequency modulation, and phase modulation. The most basic, the simplest.
Question about
Yes, sir.
frequency modulation. If we change the frequency, won't we change to another channel?
It sounds like, huh? But it's all synchronized in a way that, yes, you can be on that within that same frequency, and then it just small changes and a modification, that same thing as with power. We're going to get later down the road and look at the it's going to be within that margin. So it's going to be small variations of that. So yes, it's going to also use, as we go forward, we're going to see like the phase modulation. And yes, we will look at that, because when we're talking about 5 gig, for instance, and we're talking like channel 36, that has a specific frequency, is 5180. That's the center frequency. But within that channel, there is a whole bunch of other frequencies that are like right next to it. We'll see more of that once we start getting into the like the spectrum, okay? Because yes, and when we talk 5 gig, it's a big chunk of spectrum, 500 megs. When we talk about 6 gig, it's not just one frequency, it's 1,200 megahertz of spectrum. So yes, there's a whole bunch of variations in that. Now, the most basic, the simplest, the slowest, and the most robust modulation we use in Wi-Fi is called binary phase shift keying, BPSK. I know PSK usually sounds like pre-share key. Not here. It's another acronym that means something else. Right here, when we talk about BPSK, we're talking about this modulation, binary phase shift keying. I know, perfect topic for Monday. I know somebody will be like, it's Monday. I know. And we're going to be talking about modulations and waves and phase shift keying. Ugh, boring. Hey, I told you, man, a lot of these things are just boring. But we have to know about it. So what is BPSK? Well, binary, we're sending 1 bit per cycle. We're talking waves, so we're sending one wave. We're sending one wave, and that wave, let me just probably change the color here to, I don't know, green. We send this one wave, goes up, down, down, up to the center. And then where the crest is, like this guy right here, at 90 degrees, then if we send that wave and the crest is at 90 degrees, then we are sending a 1. Now, this area, it's called the error vector magnitude area. And what this means is that no matter where you land in this area, you're sending your data. For instance, if you send that wave and because of distance or interference or something happened, that wave kind of like makes it out there, but it's kind of like this, then the crest is still here between 90 and 180. You're within that area, then that's a 1. Then if that wave's more like kind of like this, because then you got shifted a little bit and because of the distance, interference, a car drove by and make that wave bounce, and then by the time you received it, the crest is around here, like between 0 and 90, somewhere in this area, then it's like, oh, that's a 1. So you are getting your data regardless of where you land. Error vector magnitude. That's like that area where you can land and still get your data through. Now, since this is phase shift keying, if you change the phase and instead of going from the center up, you go from the center down, then up center. That's a crooked wave here. Let me just try to make it better. Then now the crest is here at 270 degrees. 90, 180, 270. At 270 degrees, if that's where your crest is, then you're sending a 0. And same thing, you have this error vector magnitude, this area where if because of distance or interference or whatever, that wave's kind of like that, then you're landing here between 270 and 360. You're still getting your 0 through. That's a crooked one here. Let me just try it again. There we go. Kind of like that. So if you're like here between a 180 and 270, as long as you land in between this area, then you're getting your 0 through. Now, why is this lowest? Because each wave represents a 1 or a 0, 1 bit. So it's slower. Why is it the strongest? Because you can be like way off and still get your data through. It always works. That's why Wi-Fi always works. Well, most of the time, but it always works. On day one, we talked about, hey, you have an access point that is designed to be mounted like this in the ceiling and it's mounted like a clock on the wall, it still works. You put it upside down, it works. You put it upside down above the ceiling, it works. You put it upside down inside a metal box above the ceiling, it works. Yeah. And what's the most common complaint we get about Wi-Fi? It's slow. And when somebody calls you, hey, Boris, come and fix the Wi-Fi because it's going slow. Oh, it's go. If Wi-Fi is going slow, that's when you go like, yes, Wi-Fi is doing exactly what it was designed to do, to go slow or to go fast, depending on the environment. Because using this other modulation called quadrature, phase shift keying, now we are sending 2 bits per cycle. Now this, man, this is the most boring stuff to talk about. Very boring. But here, let's just try to simplify this. Modulation is just a way to transmit ones and zeros using different methods, using different mediums. We said when you have an Ethernet NIC, you're sending ones and zeros using electrical pulses on the wire. High voltage means a 1, lower voltage means a 0. If you're using fiber optics, you're sending ones and zeros using different modulations, and we're using light waves to send ones and zeros. Now let's create a new modulation right here. Boris, I'm going to send ones and zeros, okay? And I'm going to use my hands. Watch out. Let's just create a new one, okay? It's called a Fernet modulation. If I do this, that's a 1, okay? If I do this, that's a 0.
Okay.
Okay. So write down what I'm going to tell you.
Hold on.
And then read it back to me. Or Eugene can help too. Eugene's like, yeah, I can.
I'm ready.
Okay. Okay, that's it.
Okay.
What did I send?
This is B in hex 1001.
Okay, here we go. 1001. That's what I did, just using my hands. See, that's a modulation. Now, Ando.
It's 9. Sorry.
You're just going too much, man. Like hex. Who's talking hex? We're just talking binary here, ones and zeros, man. Very simple. Okay, Hando, where are you at? Where do you live? Where's your house?
In France.
In France?
Yes.
Huh, welcome. Bonjour.
Bonjour.
Je ne parle français. Sorry. So, I assume you like soccer, football, right? You like football? Mbappe? No? You're like, nah, no, I'm not a football guy. Yeah, me neither. I don't watch football. That's a waste of my time.
I'm just an IT guy. I'm just.
But hey, let's say you like football, and let's say you and I are gonna have a digital conversation, ones and zeros, okay? But for that, we're gonna use a football, okay? You're gonna be on the back of the room, and you're gonna be kicking the ball. And every time you kick the ball, you're sending a 1 or a 0. Simple enough? Okay. So let's say you have 100 ones and zeros that you need to send me, okay? Every time you kick the ball, let's say I divide this room in 2 halves. If you hit the ball and you kick it and you hit this side, just go back here. If you hit this side, that's a 1. Okay, if you kick the ball and you hit anywhere out here, can be up in my eye or down in my belly or over there, over here, anywhere on this side, that's a 0. That make sense? That good? Okay. So how many times are you going to have to kick the ball to send 100 ones and zeros? You're going to have to kick it 100 times. To send a 1, you have to kick it and hit here. To send a 0, you have to kick it and hit anywhere on this side. Does that make sense? That's another modulation. So how precise do you have to be? Well, I don't know how good you are, but you can almost be blindfolded, and then you aim in that direction and you kick the ball and you're going to hit it. So it's really easy. Not very hard, is it? Very easy. How do you say easy in French?
Facile.
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 Facile. Okay. Fácil en español. Okay. Very easy. You can be like blindfolded and wrong and not very good, and you kick it and you get the 1 or the 0. You have all this space to play. Error vector magnitude. How wrong can you be and still get your data through? But that's not very fast, is it, Hando? Because you're going to have to kick the ball 100 times. So to go faster, what we're going to do is I'm going to divide this room in 4 quadrants, okay? Because each time that you're going to kick the ball, you're going to send 2 bits. How many possible combinations of ones and zeros you have with 2 bits? Well, it can be 0, 0, it can be 0, 1, it can be 1, 0, or it can be 1, 1. So you have 4 possible combinations of ones and zeros if you have 2 bits. So I'm going to divide this in 4. If you want to send me 0, 0, then you have to kick the ball in this quadrant right here. If you're sending 1, 0, you're going to have to kick it up here. 1, 0, and 1, 1. Now, each time you kick the ball, you're sending 2 bits. So it's faster. But now, how much better do you have to be? Yeah, now you have a smaller EVM, smaller box to play. You have to aim right. You have to kick it with more precision. You have to be more precise. It's faster because now you don't have to kick the ball 100 times to send ones or to send zeros, one at a time. You're going to kick it 50 times, less, half. Because every time you kick the ball, you're sending 2 bits. Does that make sense to that point? Okay. Let me share my screen again. QPSK is that next modulation where with the same wave, we're not sending a different wave, it's the same wave. But if we agree that, hey, this wave, and actually, you know what? It's really complicated, but we're just simplifying it. Because we don't have to get into the equation level. Once, I don't understand it well enough. And second, we don't control this. This is something that devices will do dynamically. They will go at BPSK or they will go at QPSK, and then they're going to send as many bits as they can based on the experience they're having. So QPSK, it's a combination of sine waves and cosine waves, and then the least significant bit represents one bit and the most significant bit represents the other bit, and who cares? It's Monday. I'll talk about sine waves and cosine waves. That's boring enough. But hey, we need to talk about it because this is what Wi-Fi uses. And yes, I don't like to waste my time. I don't like to waste your time. We have to cover this, and trust me, all of this is going to start making sense in other classes. And this is going to be the simple way, okay? This is extremely important. We've been talking waves. Wi-Fi devices are sending waves, and we're sending ones and zeros, and we're going really fast. And in the marketing documents, you see like this is going at 9.6 gigabits per second and 1.3 gigabits per second. You're going really fast. Like, wow, how are we going that fast? It's the same waves we're sending. It's just the way they're modulated, the way we are receiving these waves that we're going to represent more ones and zeros on each transmission. So QPSK, we're sending 2 bits per cycle. Now we are dividing this in 4 quadrants. We have a smaller EVM, and here where the crest at 45 degrees is, that's where I'm sending my data, but I have a smaller margin for error vector magnitude. That's QPSK. Oh, man, this is so boring. Here, let me just try to put this in a different way. Okay. All right. So let's do this again. If we are sending, 1 bit per cycle, that's called B, binary, 1 bit, PSK, phase shift keying. Since it's binary, how many possible combinations of ones or zeros do we have? Well, we have two. It's either a 1 or it's a 0. See, this is the graph we just did. So we represent that like this. And then we have 360 degrees, 180 degrees, 270 degrees, 90 degrees. Man, this brings back memories when I was in school. Remember teachers talking to us about these waves and this like boring stuff. When are we ever going to use this in life? We're all using it right now. So if I send a wave and the crest is here at 90 degrees, then I'm sending a 1. My error vector magnitude is this entire box. Basically, anywhere in this area where I land, I'm sending my 1. So, and I'm just going back to the example we just did. If that wave's kind of like weak and kind of like out of sync, like the crest is over here, then wherever I land, I'm going to get my data through. That's a 1. If I shift the phase, phase shift keying, and then I'm going to go down, up, down. Here where the crest is at 270 degrees, 90, 180, 270, I'm sending a 0. See, because it's a 1 or it's a 0. And then my EVM box is here. That's going to be this area. Same story. If the wave, because of distance, of limitation, or interference is kind of like here, then wherever you land, you're sending your data. It's a wave, depending how it goes, depending how it's modulated, then you're sending a 1 or a 0. Since we always want to go faster, and we want to send 2 bits per cycle, with 2 bits, then we have, here, let me just put this down here. We're going to have 4 possible combinations of 1s and 0s. Be 0, 0, 0, 1, 1, 0, 1, 1. So we are using all 4 quadrants. That's what the Q is, quadrature, the cuatro, okay? We're using all 4, and yes, we're using phase shift keying. Now, we do this same representation here. 360. So now, here is where my target is. My EVM becomes smaller because now it's only half of this area, half of this quadrant that I had before where I can send my data at 45 degrees. So that wave, the crest of that wave has to be here at 45 degrees to send my data, okay? And then, yes, we're talking phase shift keying. You shift phases and move things over a little bit so you can send your data across. We want to go faster. So this one is faster, is less reliable because you don't have all this margin of error. Now your error vector magnitude is smaller. Since we want to go faster, there is another modulation that we can use in Wi-Fi. In that modulation, you can send 4 bits per cycle, 4 bits. How many possible combinations of 1s and 0s do we have with 4 bits? We have 16 possible combinations, right? It can be 0, 0, 0, 0. It can be 0, 0, 0, 1. It can be 1, 1, 0. And then if you play with all those combinations, you're going to have 16 possible combinations of 1s and 0s. Okay? 16 possible combinations of 1s and 0s. Let's come back to this representation. 360, 270, 180, 90. Okay. With 4 bits, if you're sending 4 bits per cycle, With 4 bits, you have 16 possible combinations of ones and zeros. We're still using all 4 quadrants, okay? But then, if I want to send this guy, my EVM just got smaller. If I want to send that guy over there, I have to send a wave at 45 degrees with that amplitude, okay? Also, at 45 degrees, there's this guy down here. So if I want to send this guy, of course, my EVM is smaller. Also, at 45 degrees, I'm going to send that wave. And what am I playing with now? I'm playing with the height of that wave. How is that called? Amplitude of that wave. Now we are mixing the amplitude modulation. 16 QAM is the next type of modulation we use in Wi-Fi. We can go faster because every wave represents 4 bits. Hundo! I'm going to divide this wall in 16 little squares. How much more accurate do you have to be? Yeah. You don't have this entire half for a 0. You're sending 4 bits with the same kick. It's the same ball. Doesn't change. It's one ball. But now you're going to have to hit this specific little square back here. Because if you don't hit it, then data doesn't go through. Now you have to be like really precise and aim really well. And now you have to practice more because you're not going to be able to hit those little tiny squares. Does that make sense? So yes, higher modulations represent more bits per wave per cycle. But you need better conditions. So 16 QAM, a better modulation, is faster, but it's harder. You need better conditions for this to go through. 16 QAM. Questions up to this point?
For now, I think we should kind of revise how you build the diagram on your left, because it's not that common knowledge how you convert a sine wave that is presented on the right into a cyclic diagram on the left. So how do you do it in general words? So what do you do with the signal to make it from the right side, where I can see a sine wave, into a quadrant wave?
It's angles and power levels. And yes, and it's extremely complicated. Okay, because there's a lot of equations, and I've looked at those and I'm like, yeah, good thing we don't have to worry about this. And who cares how the mechanism is? The guys that write the drivers and the ones that have to process all these digital signals, those are the ones that have to deal with this. So what we're doing here is just showing a simple graphical representation of how these waves are going and representing more things. And yes, it's a combination of sine waves and cosine waves, and it gets really, really deeper more than this. So this is
actually,
just,
what my question was not that hard, actually.
Yeah.
So,
The translation is easy, Boris. It's basically where is the high part of the wave if you are hitting that place.
I
will
know.
be in that quadrant.
My intention was to put it into the course because me personally, I can decrypt it. I know how the style works, but in favor of the course, I would like to get it recorded as well. So while it traverses the sine wave, you mark the angle you're at, and then the height, the distance from the 0 from the left quadrant is the amplitude of the wave at the moment.
Yeah, and it's not to scale. None of this is to scale, okay? If that's kind of like, that's higher than the one on the right.
That's okay, yeah.
Yeah.
But the idea is that on the left side, you represent the same sine wave, but you use angle, so the phase of the sine wave and the current amplitude. Well, not current, the most the amplitude of the wave at the point. Yeah.
Yes. Yes, absolutely. Now watch this. We want to go faster. We always want to go faster. That's the nature of Wi-Fi. So they say like, okay, what other modulations can we use? And then say like, what if we send 6 bits per cycle? So the same wave, but if we send it representing more bits, we can be going faster. So if we're sending 6 bits per cycle, how many possible combinations of ones and zeros do we have with 6 bits? Then with 6 bits, we're going to have 64 possible combinations of ones and zeros. If we are, and I'm not going to draw 64 little dots on the screen. What I'm going to do is turn this quadrant, these 4 quadrants into just one quadrant. Now at 45 degrees, now we have 1, 2, 3, 4 possible combinations of ones and zeros. So if now I want to send this guy over here, I know Boris like, that's off. That's not center. Don't worry, man. Take it easy. Now we're going to send also at 45 degrees a shorter wave, less energy, lower amplitude. And if we want to go and send this guy here also at 45 degrees, now you're going to send a shorter wave. This is what's called 64 QAM. This is the highest modulation you can obtain with 802.11a and G and N. N could use up to 64 QAM. That's the highest modulation. No, I'm going to divide this wall in 64 little squares. How much precise do you have to be? Yeah, you know what? Forget about it. You know what? How to forget about it? It gets really complicated. It gets hard. So higher modulations allows me to send more ones and zeros with the same waves, but you need better conditions. With 802.11ac, with 802.11ac, you can send that came out with a faster modulation where you could send 8 bits per cycle. 802.11ac. How many possible combinations of ones and zeros do we have? 256. And that's what's 256 QAM. Higher modulation, more bits, more ones and zeros per cycle. And that's what they say, like, yeah, with 802.11ac, you can go 1.3 gigabits per second. 1.3 billion bits per second. Billion, 1 million, 1,000 million, right? Bits per second. That's really fast. With 802.11ax, there is a new modulation where you can send 10 bits per cycle. That gives you 1,024 QAM. And with Wi-Fi 7, they came up with another one. You can send 12 bits per cycle. This is 802.11be. Wi-Fi 7. And they're talking about 4,096 QAM. Okay. Let me pause right here and let you process that. How's that for a Monday, huh?
Let me
That's
ask you
okay.
something about this. So, you need to be more precise as the QAM increases.
Yeah.
Is there any correlation, like a table or something about what's the SNR that I should have to achieve 64 or BPS key or
Kind of. Let me just show you here, and then we'll bring up. Yeah, I'll show you. There is a table. I'll show it to you. But watch this. The most basic, the most robust, the strongest, and the slowest modulation we use in Wi-Fi is BPSK. Okay. Now, why are we even talking about this stuff? Because if you're installing Wi-Fi, if you're troubleshooting Wi-Fi, you have to know about this. If you see a device going MCS 0, ooh, what's MCS? Don't worry, we're going to get to it. Then that means you're going a BPSK coding 1 of 2. You're using longer interval, 20 megahertz wide channel, then you're going to go really slow. And now you know why. Like, well, why is this guy going BPSK? Why is he going the slowest? Because maybe it tried QPSK and it failed, then it switches automatically down to BPSK. But if it's going pretty good, data ACK, the device is like, I'm going to try to go faster, send 2 bits per cycle so I can send more data faster. And then data ACK, and then it switches up to 16 QAM. And then now with 16 QAM, you're sending more bits per cycle. And then you go faster, 64 QAM, data ACK, and you're sending many more bits per cycle. Okay? And then, yes, with higher modulation, 802.11 AC, you can send more bits per cycle. But watch these guys. Now at 45 degrees, up, I had the hiccups like right when I was doing this. Man, that's a crooked line. Sorry, 40s. You're like, that's crooked. That's not how it goes. Chill, man. It's just to show the
It's
concept.
just Monday, yeah.
Yeah, it's like, that's not right, man. Yeah, it's Monday. So now you can see how much precise you have to be, because if you are just a little bit off, now you're hitting some other combinations of ones and zeros, and data is not going through. And yes, the higher the modulation, the more bits you're sending. But you have to be really precise. And these power amplifiers, sending this minuscule amount of power in this wave, the digital signal processors have to be just spectacular. This is amazing that this thing works. But that's how Wi-Fi works. And a device can go 1024 QAM, data ACK, no ACK, boom, it switches down to 256. Data ACK, no ACK, it switches down to 64 QAM, data ACK, no ACK, 16 QAM. And you're walking away from the access point. Now you're further away. Now those waves have to make it, and the device has to be able to receive them. Look at the FCS, frame check sequence, and it says you should receive 12,000 bits, and it physically does a cyclic redundancy check. Look for physical errors. And if you only got 11,999 bits, it's like, oh man, this frame is for me, but it's bad. So it does nothing. So the sender, the transmitter is like, I sent this to Boris and he didn't reply. So I assume he didn't get it. So what do? I try again. Going through those contention windows that we talked on last class. And then now I'm going to pull a bigger random number. It's going to take me longer to get to 0. And when all of those conditions meet, I will try again and resend it. And then maybe if he's not replying, maybe he's too far away, maybe the waves are not making there. So maybe I'm going to go slower. And then I switch down to QPSK, and I'm sending less bits per cycle, but now he's getting data, no ACK. I'm walking away, have more obstacles in between. Now my data is not going through, I'm not getting ACK, so I have to retry, and say like, you know what? Maybe I'm gonna switch down to BPSK, and then I'm gonna send data, and that it works every time. Data, act, data, act, data, act. But I'm going slower. Why? Because I'm sending less ones and zeros per wave, per cycle. And devices can go fast, or they can go slow. And then fast, and then slow, and then fast, and then slow, and then fast and slow. And it will change all the time dynamically based on what's happening in the air. Eugene, let's say you have to buy a switch. And they tell you, okay, you have to buy a switch that has 5 gig ports because it's going into a data center. You're going to plug in servers to it. And it has to have PoE. It also needs power over Ethernet. And then let's say you get on eBay or, I don't know, KSL, whatever website you use there to buy stuff. And then let's say brand new, that switch that you want is 5,000 euros. Okay. But then you find it online and it's only 500 euros. And it's the switch you want. It's like, there's something fishy about this switch. So you call the guy that is selling the switch and you ask, hey, I need that switch because I need 5 gig ports and I need PoE. But why is it so cheap? I know you might think like maybe it's stolen, maybe it's broken, maybe, I don't know, what's the story? And the guy said like, no, this switch is legit. It's not stolen, it's good. But the problem is that when you plug something in the ports, sometimes it would go 5 gigs, but sometimes it switches down to 2.5 gigs. And sometimes it goes at 1 gig, but then it can go back to 5 gig, or it can go at 10 megabits per second, or it will go 5 gig, or maybe 100, or maybe 1,000, or maybe 100, or maybe 1,000, or maybe 10 megabits per second. But most of the time it goes at 5 gig. Would you still buy that switch?
It depends. For data center, no.
Exactly. Why? Because you need 5 gig all the time. Yet, in Wi-Fi, devices will go at BPSK or QPSK, and they will go fast, and they will go faster, and they will go really fast, or they will just switch down to go really slow. That's how Wi-Fi works. Dynamically, devices will switch up and down when it comes to speeds based on the success or failure that you have every time you're sending transmissions. Questions or comments up to this point?
Yeah, I just wonder how many times it has to fail before it switches back to the lower modulation. Is there any number?
Nope. It depends. Man, and this gets very more complicated. Hey, I'm just trying to simplify things for you here, guys, because it depends on the programming that the driver of the device has. Maybe I send data at 1024 QAM, and I don't know, maybe after 50 failures, I switch down. And it's not just the modulation. It can be the coding, and it can be the guard interval, and it can be many other factors that might change. And maybe if I send you, when do I switch up? If I'm sending BPSK, and I don't know, if I send 10 successful or 100 successful frames, then that is going pretty good. Maybe I'm going faster, and maybe I don't know. There's no number because it all depends on how the devices are programmed and how smart they are making decisions. We'll talk more about this when we get to the green diamond or the decision matrix on devices. And we're going to see, don't worry, we're going to get today in this class to a point where we're going to see some of these changes. Now, let's talk about SNR, because yes, this level of success or failure is what's going to make us go faster or go slower. So let's talk about few terms here. One of them is SNR, but let's talk about RSSI first. Received signal strength indicator, a fancy combination of words for the signal. So if the RSSI, the signal, that's this guy, signal, if the signal is neg 50, for instance, the noise, this guy over here, let's make it red, the noise, let's say the noise is neg 95. So SNR, it says ratio, signal to noise ratio. It's not a ratio. It's actually the difference between signal and noise, that gap. The gap. You guys in England understand very well the gap. Mind the gap. That's what they say when you get in the train, the sub. Mind the gap. That gap in between signal and noise is what allows you to have good or bad communications. Let me just explain this. Right here, if the signal is neg 50 and the noise is neg 95, the difference between those two is SNR. SNR is a positive number. I know we're always talking neg 50, neg 60, neg 90, negative this, negative that. SNR is a positive number. It's just how many dBs are there between signal and noise. So right here, I would have 45 dB SNR. And I know when we talk about antenna gain, we talk about dBi relative to an isotropic radiator. That's dBi. And when we're talking about power levels, you know, the amplitude of these waves, we're talking about dBm relative to a milliwatt, okay? So 45 dB SNR is pretty good. It's a big gap between signal and noise. And then we can use higher modulations, 1024 QAM, 256 QAM, and then we can send lots of ones and zeros every time we're sending waves. If that gap becomes smaller, either because the signal goes down, if my signal goes down to, let's say, neg 65, or if my noise goes up, if let's say my noise goes up to neg 85. So now SNR is that difference. So in here, let's just put it in there. The difference between neg 65, let's just bring it over here, and neg 65, now we have 20 dB SNR, smaller gap. Now we're gonna have to use lower modulation, 16 QAM, maybe 64 QAM. If that gap becomes smaller, either because the signal goes down, let's say my signal goes down to neg 70, and my noise goes up to neg 80. Now that gap, it's 10 dB SNR. With that smaller gap in between signal and noise, we are forced to go lower modulations, PSK, QPSK. So the higher the SNR, the better the modulation. The lower the SNR, the difference between signal and noise, the lower the modulation. But let's look at this graph. I think it was Francois who came up with this. This is a good graph to kind of explain that. If you have low signal, then low signal will give you low SNR. With low SNR, you're going to be using less complex modulations. which means that you are sending less ones and zeros every time you're sending. So you are going at lower speeds, which means that every time you have something to say, you are utilizing the airtime more. So it's going to take you longer to say whatever you have to say. Does that kind of make sense? Pretty straightforward. The opposite, saying that you have a strong signal, you have high SNR. When you have high SNR, you can use more complex modulation. With more complex modulations, you can send more ones and zeros every time you send a new wave. And when you have something to say, you just say it and get off the chat. So you use airtime less because you're sending things fast and then you get off. Then you send fast and then get off. Freeing up airtime for other devices to send their waves. Here's the problem with this. Strong signal does not necessarily mean high SNR. How many times have you gone to a place to fix a Wi-Fi problem? Wi-Fi is really slow, but I don't know why, buddies, because I have 5 bars on my phone. What does 5 bars mean? That you're getting good signal. But that doesn't mean that you're going to go fast. Because what happens if the signal is neg 65? What happens? Well, let's say, what happens if the signal is neg 50, but the noise is neg 60? Then your gap is still 10 dB. Is that gap? It's not if the signal is strong or if the signal is weak. It's what is your signal to noise ratio. 5 bars, strong signal, doesn't mean you're going to get good Wi-Fi. It just means it's loud. Let's say Alejandro and myself are going to have a beer after class. Okay. And then we're walking down the street and it's quiet and we're talking, hey, how's it going? And we're just, sending lots of words every time we're talking. And then we go in the bar and it's really loud because there's live music and there is football, La Copa Mundial, and then there's games, and then it's just really loud, and the noise floor goes up. And it's so loud that now I am talking to Alejandro the same way I was walking while we were walking on the street. And said, yeah, I was just going to ask you about the class. And he's like, what? I'm like, the class. I'm like right next to his ear, screaming, and he still cannot understand what I'm saying. Can you relate to that? The fact that I'm screaming doesn't mean he's going to understand what I'm saying. If the noise is so high, I'm going to have to change my modulation. How do I change my modulation, or how do I compensate for the noise? I get closer, scream louder, or I send less words every time I talk. But let's say Mark and I are going to run a cable. Okay. Mark, you ready? Sorry, wake you up to run a cable, man. I know it's early in Texas, but it's earlier in Utah. But let's say Mark and I are going to run a cable. And we're here talking, say, okay, here's the box. And say, okay, Mark, I need you to go all the way to the end of the hallway. And then there is a pull string. I need you to start pulling on that string, and I'll start feeding the cable over here. So, okay. And then he walks all the way down. He starts pulling the cable, and then I get a kink on the cable, and they get stuck. Now I cannot turn around and say, like, hey, Mark, do you mind not pulling the cable right now because it gets stuck on the wire? Because he's so far down that he's like, what? Like, the cable, don't pull because it's stuck. Like, no, don't pull. I scream loud. I send less words so that those waves get there and they don't get on top of each other and he can understand well. I'm modulating at a lower modulation. I'm sending less words, less waves every time I talk. Can you guys relate to both examples? Because that's exactly what Wi-Fi devices are doing. Wi-Fi devices will go fast or they will go slow based on their success or failure rate. What's the rate? I don't know. Each device gets programmed differently. And these are the tables that you were asking for. Well, kind of. Let me just get out of this guy. Hang on. How do I stop this so that I can come back here? Was it you, Alex, asking? Somebody was asking about what's the SNR?
Yeah, it was me. But the problem is the MCS index in the internet. They don't have the SNR and RSSI columns. They only have the rest of it.
Yeah. You don't find it like everywhere or precise and all of these numbers we talked about in that session about NICs, network interface controller, like how do devices calculate the signal they receive? How do they calculate the noise? And if they all have different ways to calculate the signal and they all have different ways to calculate the noise, how is that SNR going to be a metric that is going to tell us the absolute truth about how good or bad this transmission is? So it's kind of like a metric that people use, and you see it in data sheets. This device needs, 20 dB SNR for a voice conversation to go through. 25 preferred. And we recommend better than 25 SNR. And yeah, we talk about these numbers, but it's like, it's just numbers. So let's talk about these MCS tables. Back when we had 802.11a and 802.11g, the speeds that you could possibly get were pretty straightforward. You could only go up to 64 QAM. Okay? The coding, let me see, the coding, see this column right here? I don't know, this is complicated, but just in simple terms, meaning coding 1 of 2 means that you send 2 bits for every bit you want to send. So you send 2, and out of the 2, you get 1. So it's very redundant because you send 2 every time and you get net 1 out of the 2. But it's not very efficient because you have to send 2 bits and then you net 1. That's coding 1 of 2. The other type of coding that we use is 3 or 4, meaning you send 4 bits and out of those 4, you're going to use 3. So you lose 1. It's more efficient, but it's not as redundant. It's kind of like the party bit we used to send, another communication. A party bit, remember those fax modems and those transmissions? Coding, there's coding 2 of 3 and 5 of 6. So 1 of 2, 2 of 3, 3 of 4, and 5 of 6. That's it. Those are the 4 different types of coding. Same principle. Coding 506 is the most efficient because you send 6 bits, and out of the 6, you get 5 net. So back in the day, with A and G, you had up to 64 QAM in the codings, and the speeds were pretty straightforward because it was only one spatial stream. Let's talk about spatial streams right now. If I have an antenna, let's just say, pretend. Let's say I have to send Dan these 4 batteries, okay? I only have one hand, and I can only send 1 battery when it's my turn. I make sure nobody else is throwing batteries. I'll make sure that there's no energy interruptions in the air. I make sure nav is equal 0. I'll go through the whole contention process. And when it's my turn, since I can only send 1 flow of data, I will throw 1 battery at him. This is what's called SISO or SISO, single input, single output. If it is my turn, I will send Dan 1 battery, and I throw this battery at Dan. Dan can only receive 1 battery at a time. So when it's my turn, I will send 1 flow of batteries. Throw one battery at a time. That's one spatial stream. CISO, one spatial stream. One flow of data, one battery at a time. Boom. So how many times do I have to go? Well, I have to wait for my turn. And when it's my turn, make sure nobody else is talking, no energy in the channel, nav is equal 0. And I pull an F, I pull a random number and count down to 0. And when all those conditions meet, then I send another battery, one spatial stream. Boom. And then again, make sure nobody's talking, there's no energy in the channel. And then when it's my turn, one flow, one spatial stream, I can only throw one flow, one battery. And then the fourth one, wait for my turn, make sure nobody's talking. See, this is Wi-Fi transmitting. And then when it's my turn, since I have one antenna chain and I can send one flow of data at a time, then I send it. That's one spatial stream. Does that make sense? Okay. N comes about. 802.11n. Then with 802.11n, that's why it's my favorite, because they added so many more things. They say like, oh, how can we make this Wi-Fi thing go faster? And they say, well, remember one of the things was the guard interval? That when you're sending waves, if I'm sending then a file, a 10 meg file, I'm not sending the whole thing at once. I break it into chunks, and then I'm going to send groups of waves, a symbol, 3.2 microseconds worth of waves, wait 800 nanoseconds, and send more waves, 3.2 microseconds worth of waves, and then you get the data. And then they say like, 800 nanoseconds I have to wait in between symbols, in between waves. How can we make this faster? And they said, well, how about we send this group of waves, and then instead of waiting 800 nanoseconds, we only wait 400 nanoseconds, short guard interval, and then we send more waves faster. That good? That's one of the improvements. They came out with short guard interval. Instead of waiting 800 nanoseconds in between symbols, we only wait 400, then send more waves faster. They also said, how about if instead of just being able to send one spatial stream at a time, we figure out with all these really smart engineers how to send multiple flows of data. So if now I have two antennas and two radios that can process those signals, when it's my turn, now then you are a two spatial stream device. I'm a two spatial stream device. When it's my turns, I will send two flows of data. No, I'll send two batteries at a time. Boom, there we go. And then here we go. You get them right there. Look at that. They're even the same. Are those Amazon batteries? Probably they are, huh? Rechargeable.
Yep.
Okay.
Rechargeable.
And here I go. It is my turn, because I already made sure nobody's talking. There's nobody in the channel. Made the nav is equal 0, pull the navs, pull a random number, get down to 0. When all those conditions meet, I can send two flows of data. I throw two, and then now Dan can receive two, and then we're done faster because I'm sending two flows of data when it's my turn. This is oversimplifying MIMO. Multiple input, multiple outputs. Now, if that will be a 2x2 device. I'll just put this in the screen a little bit. If I had 3 arms, I'll show you what a 3x3x3 device looks like. But I don't have 3 arms. But you get the concept. So that's one of the other improvements that came with 802.11n. The ability to use multiple spatial streams to send and receive data. So let me come over here.
Just one question. How about the modulation of each stream? It's different between each one, or maintain the same modulation for the
they'll be all the same. Now with 802.11b and Wi-Fi 8. I think Wi-Fi 8, one of the things is that you can use different modulations per spatial stream. But what I'm talking here is all of the spatial streams will use the same modulation. When it's my turn, I'll use the same modulation on all of them. So let me, oh, not you, hang on. You have probably seen this. Like in data sheets, you see a device is a 1 by 1 by 1, or a 2 by 2 by 2, or a 3 by 3 by 3, or a 4 by 4 by 4. That's how it's read, but it should be like 4 times 4 colon 4, I guess. I don't know. 4 by 4 by 4. What does this mean? In Wi-Fi, if a device is a 2 by 2 by 2, for instance, the first digit means that I have this many radio chains to transmit. The second number means that you have this many radio chains to receive. And the last number means, and I can handle those many number of spatial streams, of flows of data. So you can have access points that are 4 by 4 by 4. They have 4 radio chains, they have 4 radios to process these signals, and they can send 4 flows of data at a time. And you might say, this has been a topic of discussion for many years, because people say like, well, but why do I need to buy 4 by 4 access points if all of my clients are 2 by 2 by 2s? Well, there's actually gains about this. This is a good thing. You want to get the access points that have the highest number of possible radio chains. If you have an access point that is a 4 by 4 by 4, and the client is only a 2 by 2 by 2, this guy's going to send 4 flows of data with the 4 antenna chains and antenna elements it has. It sends those 4 flows of data. The 2 by 2 device, MIMO, not only you can send multiple spatial streams, there are other things like maximum ratio combining. You can combine like these 2 and those 2, and now you have 2 really good ones, and then you receive those 2 combined. Or out of the 4 you get, you're going to get the best 2. And then if you are a 1 by 1 by 1 device, MIMO, that means that you can combine and get the best out of those. So there is benefits to having APs with higher number of transmissions, radio chains, 4 by 4 by 4, and smaller ones. Now, why don't we have 4 by 4 by 4 phones? Because each radio chain is going to require its own radio, its own antennas. And then if most phones are 2 by 2 by 2, and when battery goes down, they switch to a 1 by 1 by 1. They just turn one radio off, one radio chain. And then imagine a phone that is a 4 by 4 by 4, needs 4 radio chains. The processing that it needs to process 4 spatial streams, it will get really hot. It will burn through the battery really quick. And it needs more space because you have to put more antennas and more radios and more chipsets in the device. That's why we don't have devices this many. And as a matter of fact, 802.11be, the Wi-Fi 7, they were talking about 16 spatial streams at one point. They said, like, I'll just leave it at 8. 8 spatial streams. Like we don't have, I mean, there are access points out there that are 8 by 8 by 8. But yes, they have the space, they have dedicated PoE, they have lots of antennas, more processors, more everything. But that's what these numbers mean, okay? When you're looking at a data sheet and you say, oh, that's a 2 by 2 device, or it's a 1 by 1, or it's a 3 by 3, or a 4 by 4 device, this is what it means. Questions up to this point? Okay. Yeah.
Pernay, are we talking about multi-user MIMO?
Yeah, this is MIMO.
Multi-user MIMO. When you go
Oh, no. Oh, multi-user MIMO, that doesn't work. That's marketing. It never worked. I mean, I've never seen it working. Let me just tell you about multi-user MIMO. Okay, so this is MIMO. Okay, multi-user MIMO is something that came with 802.11ac. Remember, in Wi-Fi, only one device sends waves at a time in a channel. With multi-user MIMO, say, oh yeah, we can have an access point send waves to multiple users at the same time. People are like, that's unheard of. And they say like, yeah, but it has to be that this, let's say I'm going to send data to handle and bodies, okay, at the same time. So for multi-user MIMO to work, it has to be like the same type of frames. They have to go out at the same time. They have to be the same size. And handle and bodies have to be in separate, different physical locations. Because if handle and bodies are in the same area, like right next to each other, when I send waves to handle in one of these multiple spatial streams, let's say if I have a 4x4, people say like, oh, so I can use 2 of those for handle and 2 for bodies. Oh, yeah. But then they have to be on separate, different locations. Because if you're in the same location and I'm going to send these waves for handle and this wave for bodies, and they're in the same physical area, how do you know which waves are yours? Well, you don't know because you're getting all of them. And remember, in the air, they're just waves. So you have to be separated. And then I can focus the energy. This is for you. This is for you. So basically, it had so many ifs. If the frames are the same type, and if the frames are the same size, and if they're going at the same time, and if these guys are in separate locations, then multi-user MIMO works, and it's only downstream from the access points to the clients. So basically, if the stars align in the universe in a specific way, that would work. If not, I never saw this working. Maybe guys at lab environments got that to work, but I never saw any data. So yeah, it's like, it doesn't work. We'll talk more about this when we get to 802.11ax, because with AX, we can have multiple devices sending or receiving data at the same time. But we're not using MIMO. We're using different mechanisms. So back to here. Today, we have covered so far. Don't worry. We're going to put everything together. Modulations. Now we know what modulations are. BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM. That's the modulation. Talk about the coding. And then we also are talking now about spatial streams, these flows of data we can send. Now, with 802.11n, they also make this Wi-Fi thing faster and better. We can use multiple spatial streams. We can use short guard interval, a gap in between transmissions. We can, how about instead of using a 20 megahertz wide channel and sending waves in that 20 megahertz wide channel, what if we join 2 20 megahertz wide channels and form a 40 megahertz wide channel? Wider, more sub-carriers to send waves and energy in all of them, so we can go twice as fast or more than twice as fast, because some of the subcarriers that were null, now they're data, and now we can send so much more data when it's my turn. Multiple spatial streams, wider channels, short guard interval. We can go faster. So A and G using OFDM, which is the method to, we're going to talk about this later. Using OFDM, they had it easy because they said, like, look, our speeds are this. If you're using BPSK, you can go at 6 or 9 megabits per second. If you're using QPSK, depending on the coding, you can go at 12 or 18 megabits per second. If you're using 16 QAM, there are 2 different codings we can use. You can go at 24 or 36 megabits per second. And if you're using 64 QAM, which is the highest modulation we could use, then depending on the coding, you go at 48 or 54 megabits per second. That's it. Those were the possible speeds you could get with an 802.11a or 802.11g device. That's it. It was single spatial streams, SISO, single input, single output. It was only 20 megahertz wide channels. It was only long guard interval. That was it. 8 speeds, 8 possible speeds, depending on what's going on. 802.11n came. And let's just leave this at one spatial stream with a 20 megahertz wide channel. And as a matter of fact, since we could only do 64 QAM, let's stop right here. That the screen okay for you? Okay. Now with N, how are we going to list the possible address we can have? Because, hang on. Because, let me change the color. Here, let's see if this can be seen. If we have a 20 megahertz wide channel, you could now have either longer interval, 800 nanoseconds in between symbols, or you could have 400 nanoseconds. And you can have any one of these BPSK, QPSK, 16 QAM, 64 QAM modulations, and these different codings. So we're going to have so many addresses, so many possible. How do I have, hang on. There we go. We're going to have so many possible different speeds, because if you're using shorter interval or longer interval, or if you are on a 40 megahertz wide channel, because now we can join 220s, then the possible speeds we're going to have are going to be in between 6.5 going at BPSK, 800 nanoseconds, 20 megahertz wide channel, all the way to 40 megahertz wide channel, shorter interval, 64 QAM. So basically, we have all of these possible speeds in between. They say, how are we going to list them? They say, well, let's create a table and let's just create these indexes. And then if you have MCS index of 0, what that means is that you can, you are going to be going at BPSK, coding 1 of 2, and now the possible speeds come up. If you are at MCS index 0, that means you're going to BPSK coding 1 of 2, but it can vary and be 6.5 megabits per second if you're at 800 nanoseconds guard interval, or 7.2 megabits per second if you're at 400 nanoseconds intervals if you are at short guard interval, 20 megahertz wide channel, or you can go at 800 nanoseconds with a 40 megahertz channel getting 13.5, and then 15 megabits per second if you're going to. So these are all the possible combinations of speeds you have at MCS index 0. And then if you're going MCS index 7, so they added an index to it. And they say, well, that means you're going at the highest modulation, 64 QAM, coding 5 of 6, and then depending on if you're on a 20 megahertz wide channel or 40 megahertz wide channel, shorter interval, longer interval, then you're going to have these possible different speeds. Does this make sense? Questions, comments, insults up to this point? Okay. Now, they also created, because now we had multiple spatial streams. Not just one, we could go up to 4 spatial streams. So if you are 2 spatial streams, and now this thing is all over the place. Let me just move this guy and see if I can line those. Oh man, I just made it worse. Here, let me, I don't even know how to turn it. Oh, here we go. Okay. So now with 2 spatial streams, here, let me just clear all of this text over here because it's just, there we go. With 2 spatial streams, then now you had MCX index of 8 through 915 going BPSK, QPSK, QAM, and same modulation, same coding, but now with 2 spatial streams, 2 flows of data. So yes, you can go faster. And then with 3 spatial streams and with 4 spatial streams. Now, Why are we even talking about this? Because we just get out of this thing over here. Because we clear this and close that and close this window. There is a website, mcsindex.net.
It's on the chat, basically, by the way.
Oh, perfect. Thank you very much. And now, yes, there are different ones in there, but let's just see how then we can use this. Watch, I have a Mac. If I click on the little Wi-Fi icon up here, I see that I'm connected to a Home 5 network. If I hold my Option key and click on that guy, it says right there that my IP address is that's my gateway, that's the MAC address of my NIC. I'm using WPA2. The BSS ID, that's the MAC address of the radio where I'm associated. That's the MAC address of the radio. I'm on channel 52. It's a DFS channel, 80 megahertz wide channel. With 802.11 AC, they say, like, how can we make this better? Well, remember the end guys that they joined two 20 megahertz wide channels together? Why don't we add 4 20 megahertz wide channels to create an 8 megahertz wide channel? Wider channel, more subcarriers. We can send more waves faster. Then there's 80 megahertz wide channels. Country code US. This is my signal, NEC 40. Transmit rate 266 megabits per second. Oh! 1,200 megabits per second. Never mind. Sorry. Then I am at MCS index of 11 AX 2 spatial streams, number of spatial streams. Again, 2 spatial streams. So I'm going to be, this is 1 spatial stream. This will be 2 spatial streams. MCX index of 11. Let me just move this guy to the right a little bit. Let me make this smaller. Let me make it bigger. And let me move. Come on, where's the rest of my window? Like I'm missing one of these columns in here. Hang on. Okay, and with 2 spatial streams, okay? MCX index of 11. So that's going to be 0, 1, 2, 3, 4, 5. Am I missing another column over here? Hang on one second. Ah, stupid thing. Hang on. Let me open a new window and see if it resets my stuff. MCXindex.net. Okay. MCX index. So the one I had over here, I know that's probably too small on your screen. MCX index of 11, I'm 1,200 megabits per second. 2 spatial streams, so I'm going to be in this area. See? 11 is my MCS index. Now I read that there. I'm going to 2 spatial streams, 1,024 QAM. And if I come in this direction, since this is an 80 megahertz wide channel, I'm on an 80 megahertz wide channel, 40, 80. Oh, come on. Where's the rest of my stuff? Well, over here, why am I having a hard time navigating this stupid web page? Hang on. That's really small now. And still I'm missing half of my stuff. Over here, there's the 1200. Let me just try to switch this in here. Move this to the side. Make this window bigger this way. 1200 is over here somewhere. Hang on. What the hell is going on with this page? I don't know. It's over here, but let's just simplify. When I'm looking, let's say if I had 200 and let's see if it's different right now. It's still 1200. Give me 1 second. Let me bring this guy back into place. Okay. We were here at MCX index of 11. Then, depending on the data rate that I have, I read this backwards. And let's just oversimplify this. And let me give you a real life example. I went to a place where the clients would not connect at more than 22 megabits per second. Okay. 22 megabits per second, it's about here. If I have 22 megabits per second, like 21.7 is what it was. See right here. So how do I read that? I read it up. Like I'm on a 400 nanosecond guard interval, 20 megahertz wide channel. Okay. If I read that to the left, I'm going coding 3 or 4, and I am using QPSK as my modulation. I'm using one spatial stream, MCS index of 2. That's what 21.7 megabits per second mean, that the device is going to that. Now, this was a client where they had phones. It was an 802.11n network, and they were using 20 megahertz wide channels in the access points. They were advertising that. So if I'm on a 20 megahertz wide channel, what that means is that I could be going anywhere in this box. Okay? Anywhere in this box. I could be going 72 megabits per second. That's the maximum I can do with a 20 megahertz wide channel in N, one single spatial stream. Why weren't devices not going to 72? Because 72 megabits per second means short guard enable, 20 megahertz wide channel, coding 506 at 64 QAM. Maybe they tried and failed, and then they moved down to 65, going at longer enable, still 64 QAM, coding 506. And then maybe they failed and then move up, and then maybe it came up here to 52 megabits per second, going 64 QAM, same modulation, different coding, different guard enable. Maybe they fail. And some devices will just go and start bottoms up, 6.5. And then they say like, oh, 6.5 is the slowest I can go in a 20 megahertz wide channel, 800 nanoseconds, coding 102, BPSK, one spatial stream. And if it's going data, oh, this is pretty good. And then they start working their way up. And then maybe move to 7.2 megabits per second going at a short guard enable. And then maybe went up to QPSK. And then maybe went to QPSK with coding 3 or 4, 21.7. And it was maybe data, NOAC, data, NOAC. It's like, oh, yeah, I'm losing like 3% of the data I'm sending. I can live with that. That's good enough. And maybe the devices did not go past 21.7 megabits per second because they were programmed. So like, hey, if your data loss, if your retry rate is about 3-5%, then stay right there. Devices would not go any faster. But then now, if you see an MCS index less than 5, like 4, 3, or 0, or 1, now you know, like, oh, what that means is this device is going to be PSK or QPSK. Why isn't it going at 64 QAM? Maybe it's too far from the access point. Maybe the access point is upside down inside a metal box above the ceiling. Maybe the waves I'm sending from here are not good enough and not being received well enough. So the device is not receiving the data and is not confirming. So I have to retry. And it is my decision to switch up or switch down to send my data. Let me clear all the drawings in here. Windows guys. So if you're on a Mac, option click up here and it will tell you, notice I'm at 286 megabits per second. From 1,200, we're down to 286. So Windows guys, to look at this data on a Windows machine, open the command prompt. Here, let me open the command prompt. And type this command. NetSH, NetShell, WLAN, show interfaces. Go to command prompt and run NetSH WLAN show interfaces. In the chat, I'm going to place a document for you. It's a PDF document that has all of these guys. Hang on 1 second. Okay, who ran it and what did you get and transmit rate?
I'm running wired Wi-Fi.
Oh, you're smart. If it's wired, it's not Wi-Fi, but you're a wired connection. That's good. Smart man.
Well,
Okay.
in Russia we call it wired Wi-Fi.
Wired Wi-Fi.
Yeah.
Okay, so Ned, if you're on a Mac, just click, hold the Option key on a Mac on the keyboard and click up here, and then it's going to give you all these statistics. If you're on a Windows, on the chat, I just placed this document. It's a PDF, and it has all the net shell commands that will give you. We're looking at the first one now, interfaces. So who has a Windows, who has a Wi-Fi connection, and then what did you get as the transmit rate? Anybody?
I will turn Wi-Fi now. I will try to show you something.
Okay, so 173.3 is one Arguidos Costara's got, and Dan got 200 mega. So let's look at 173.3. If we go back to MCX, so 173.3.
Just pasted it on the chat.
Yes. So let's see, 173.3. Oh, the table?
No.
Oh, you just
the-
pasted bodies. Okay, here we go.
I pasted your table actually, so the one you were looking for.
Okay, perfect. So this guy, right? 1,200. 800 nanoseconds, 80 megahertz wide channel. And then I was going 1,024 QAM, 2 spatial streams. That's where that comes from. So that's how we read that, and that's what that means. So in Windows, like Boris just listed. Oh, but you are hardware on radio. Okay, let's see. Okay, here's another one that Alex posted. Oh, they posted the text, and you guys cannot see that text. Okay, so let me copy.
I
This
can
guy.
send the print screen as well.
Yeah, get a here. Let me just. I just pasted what you sent.
You can paste mine as well.
This one's good because we just need a couple to do the example. So this one is the la tasa de transmisión, the reception, is at 287. So let's just look at a 287, 173. So 287, where is 287? Here, so we do a search. There 287 here somewhere. Ah, yeah, let me just see if 173 comes up easier. Okay, there's a 173 right here. Now 173.3, there is one over here, there is one over here. So you're either on 160 megahertz wide channel, 2 spatial stream 256 QAM, or you are on 256 QAM, coding 3 or 4, not 506, and you are on a 20 megahertz wide channel. So there should be also another 173 over here. See that? So which 173 it is? This one is with 2 spatial streams. This one is with 3 spatial streams. So let me show you on a Windows machine how to find out how many spatial streams your device has. Because on a Mac, it's really easy. Option click, it says right there, 2 spatial streams. I would know I'm on this area. But on a Windows, you're going to have to run this command. Do an up arrow and say netsh WLAN show all. Then run it again. And towards the bottom, it's going to go pass a whole bunch of stuff. Towards the bottom, it's going to say number of spatial streams. How many do you have? Ooh, Ned is just showing off. It's like, I'm at 2.4 gigs. Wow. Some Wi-Fi 10. Ooh. Well, let's look at 2.4. Yeah, where's that stuff? .4 here, you're going to be like 160 megahertz wide channel. Why am I having such a hard time navigating this stupid website today? It doesn't let me scroll the way to the right or the left.
Try a different browser, probably an
Yeah,
update in the
probably.
browser.
So Alex right there posted, if you look on the chat, see right there, it says number of flujos espaciales. That is spatial streams, 2. Okay. One last thing. On this website, towards the bottom, there is the math behind those data rates. See, to get the data rate, you get a number of subcarriers, number of coding bits, and the coding, and the number of special streams, and the symbol duration, and then the guard interval duration, and that's how you end up with those data rates. Okay? So if you want to spend more time doing that, be my guest. Go for it. And that's what that means. See, if you were here at 2,400 something, so you're in 160 megahertz wide channel, 3.2 microseconds of guard interval, 1,024 QAM, 2 spatial streams. So when you are looking at a data rate, and don't worry, later in another class, when we get to packet analysis and we're capturing data, we're going to see the MCS indexes. Then now you know where that comes from and what that means for us. High MCS, anything above 5 is good. That's where you want to be. And anything below that, that means you're going to 16, QPSK, BPSK, and low codings, and then you're going to go slower. Why? Because there's something wrong. That will help you identify, like, why is this guy going at BPSK only all the time? MCS index of 0. Then that's what MCS is. It's modulation and coding schemes, MCS. That's what MCS stands for, modulation and coding schemes. It's a combination of modulations and the coding and the channel width and the number of spatial streams and the guard intervals, all the different ones that you have. So that, my dear friends from all over the world, Brazil, France, England, Russia, and everywhere else, the US and whatever you are, and whatever you're watching this from later in the future, is what modulations is all about. And that is the section that covers the modulations we use in Wi-Fi. This is one of those boring sessions that we have to talk about it because, hey, you know, we're designing Wi-Fi, we're troubleshooting Wi-Fi, we're installing Wi-Fi, we're selling Wi-Fi, we're buying Wi-Fi. This is how Wi-Fi works. Okay. With this, my friends, I think we get to the end of session 344 of Tesos and Wi-Fi. I know the 4th, 5th, or whatever session we have of this free wireless design or Wi-Fi design class that Wireless LAN Professional has delivered to thousands of professionals in the world, now being delivered here live. Well, not if you're watching this later, but being delivered live to people from all over the world, 100% free, like 98% in English. Happy Monday! Free love for everybody and free Wi-Fi training for everyone. Have a great rest of the day.
You
Thank
too.
you very so
Bye-bye.
much. Bye-bye.
All right.
Thanks. Bye.
Cheers, Pedro.
Take care. Cheers, mate.
Cheers. Cheers, mate.
There we go.
That's how we talk in London.
Yeah. Take care.